So we've practiced splitting the middle term. Now we're going to look at what happens when there are special ones. It's kind of handy to remember how these quick little patterns. However, you can always go back to splitting the middle, even though problems like in number 1 where it's set up, it doesn't have a middle term. We talked about that in class or on the video, is if there is no middle term, that middle term is really 0. And so you can use that for B to split the middle. But recognizing and understanding the two special patterns here will save you some work in the future. So first we have the difference of two squares. The difference of two squares is when the first term is a perfect square, the second term is a perfect square, and the middle is a subtraction sign. It will always split up if it's two perfect squares being subtracted, and that includes the x, the variable as well. It has to be x squared, or the square. It could be like x to the 4th. That is a perfect square as well. But it will always split into the square root of the first term. So a squared, its root is a. And we split that up and write it twice, one in each set of parentheses, and then the second one becomes the square root of the second term. The only difference is one of them will have a minus sign between them and one will have a plus, so that when you FOIL it out, your inner terms will cancel out. You'll get, if you FOILed it out, you'd get a squared, whoops, didn't write that correctly, minus ab plus ab minus b squared. The middle terms cancel out, and you can always double check. This is a squared minus b. So that's our first pattern, and we'll look at some examples in a moment, and then we're going to take some time and practice in class. Okay, the next one is a perfect square trinomial. This one is a little bit harder to recognize. Some of you notice the first term is perfect square, and so is the last. It's harder to figure out if it's 2 times the first term times the last term. So it's not as commonly used as the difference of two squares. However, good to know. Now you'll see here that the pattern then breaks into, as you factor it up, it really becomes the square root of the first, a squared, becomes a, the square root of the last, and then the middle term factors out, and it becomes just a plus b times a plus b, and we abbreviate that by writing a plus b squared. The only difference on the second one is there's a minus sign here, so there's a difference. It's a difference of perfect squares. Looking at factoring and how we can do this a little bit faster and a little bit better, but again, you can always use splitting the middle. So let's look at an example. Now, clearly this has to be a difference of perfect squares because it's two perfect squares, the 4 and the 25. The x squared is also perfect. These are not two perfect squares. This is your trinomial setup, and it will factor in to a difference of perfect squares. Okay, so a difference, wait, hang on. A difference, I'm sorry, not a difference of perfect squares. I want to watch my terminology there. It would be a difference of two squares times each other. So it does make a square. It's just different. So let's take a look at the first one. Let me see if I can move this up and over, shrink it down a little bit. 4x squared. If I were factoring this according to the pattern, I would set up my two parentheses, and then I just do the square root of the first term. The square root of 4 is 2. Square root of the x squared is x times x. And then I do the square root of the last term. Square root of 25 is 5. So I break that up. And then I need to put a sign between those. They will be opposite signs so that the middle terms will cancel. And here we have them factored out. Okay, first example. Let's look at the next example. This one is a trinomial. So if you need to, refer back to the pattern. The pattern is the first term and the last term should be perfect squares. Okay. The middle term is a combination of the first root times the second root doubled. So let's look and see if that's what we have. Up here we have a perfect square. 9y squared, it breaks down into the roots of 3y times 3y. So as we go to factor this one up, our first term should be 3y. Now let's look at the last term. It is also a perfect square. 16 breaks up into 4 and 4. So that goes here. Now, all I have to do is just double check. Either I can FOIL my new setup here, FOIL it together once we put the signs in, or just double check that this 24y is 2 times 3y, that first root, times 4. Well, 2 times 3 is 6y, times 4 is 24y. So we have that pattern. It's a plus sign, so both of these become plus signs. Since they're a perfect match, they make a perfect square, a sum, and it's 3y plus 4 squared. Last but not least, we have one more example, and the example is 49m squared minus 14m plus 1. So let's look at the roots. We have 7m times 7m. Over here we have 1 times 1. So let's see if 14 breaks up properly. It has to be 2 times 7m times 1. And it works. 2 times 7 is 14, times 1 is 14m. So the only difference this time would be 7m and 7m, 1 and 1. And since we have a minus sign in our equation, this time both of these are minus. And we end up with the perfect square of 7m minus 1 times itself. Final draft. The end. All right, so now we're going to break and do some practice problems on some, special patterns in factoring. And again, some of them will be special and some of them won't.